Hello everyone. During the previous class, we have studied the types of consolidation settlement that occurs within the soil. In this lecture, we are going to study how the consolidation test is being carried out in the lab. So first of all, let us study that what you mean by consolidation test, or what does the test consists of. Normally, consolidation test consists of applying the pressure on a thin soil sample in increments and keeping each pressure increment for sufficient amount of time until the consolidation of the soil specimen and the measurement of the vertical deformation of the soil specimen due to expulsion of the pore water carries on. Main consolidation parameters such as coefficient of compression, coefficient of volume change that we have discussed, as well as coefficient of consolidation, can be determined from this consolidation test under a certain pressure increment. So let us first go through the equipments which are used for the consolidation test of the soil. Mainly, the consolidation properties required for calculation of the consolidation settlement are obtained by conducting a consolidation test on a soil specimen in a geotech laboratory, and the apparatus used for conducting the consolidation test is known as consolidometer, or in other terms it is also known as odometer. So this is the figure. This figure shows a sectional elevation of a fixed ring consolidometer. Generally, it consists of a cylindrical consolidation ring which is 6 cm of internal diameter. It is made up of gunmetal or stainless steel. The consolidation ring is placed in a consolidation cell. A soil specimen is cut from the undisturbed soil sample to the size of the internal diameter of the consolidation ring, and it is placed into the consolidation ring. The porous disc of the same size of the soil specimen is placed above and below the soil specimen to represent the pervious or the drainage of the soil in the feed layer. The top porous disc is just a little less than that of the soil specimen in diameter. The bottom porous disc is bigger in size. Filter papers are cut into the same size as that of the soil specimen, which are used between the soil specimen and the porous disc to permit the flow of water from the specimen during the consolidation test and prevent the penetration of the fine soil particle into the voids of the porous disc. A pressure pad and steel ball are placed over the top of the porous disc in the cell. So this is the sectional elevation of a fixed ring type consolidometer. So what are the different type of consolidometer? Here you can see in the next figure, this is a floating ring type consolidometer. Mainly there are two type of consolidometer. One is a fixed ring consolidometer, another is the floating ring consolidometer. So what is fixed ring consolidometer? In this figure, or in this type of consolidometer, the specimen ring as well as the bottom porous stone are fixed in position. The soil specimen moves in the downward direction relative to the specimen ring during the consolidation. It is possible to monitor water from the base of the bottom porous stone in the fixed ring type consolidometer. So what about the floating ring type consolidometer? In this type of consolidometer, the specimen ring is not fixed in position. The soil specimen moves both in upward and downward direction relative to the specimen ring during consolidation. The advantage of this floating ring type consolidometer is that the skin friction between the soil specimen and inside surface of the specimen is less compared to that of the fixed ring type consolidation. So now, how this test proceeds, or how the test procedure takes place? Normally, the consolidation cell is mounted on the loading platform of the odometer, and a loading yoke is used to facilitate the application of the load on the soil. In this figure, you can see easily the consolidation test apparatus. These figures indicate the consolidation test apparatus, where the consolidation cell can be seen, the platform can be seen. Actually, this is a figure of a 3-gang consolidation apparatus where 3 sets of consolidation can be done consecutively. So there is the small water reservoir and the dial gauge where the deformation can be measured. This is the consolidation cell, and there's the platform. and they are the weight which are used for application of vertical stress. And the dial gauge which is present in the instrument having a least count of 0.002 mm. It is mounted on top of the pressure pad to record the compression of the soil specimen. So how this test is being carried out? What is the process of this test? Initially, a load of 5 kN per meter square, which is also known as the seating load, is applied on the soil specimen to adjust the unevenness of the surface of the soil specimen. The seating load is maintained for 24 hours or 1 day and then it is removed. The load is again applied on the soil specimen in increment using a load increment ratio of 2. The load is applied by placing standard weights on this loading arm of the odometer, as you can see in the figure, to cause the required final sets of 10, 20, 50, 100, 200, 400 and 800 kN per meter square on the specimen in successive load increments. The settlement dial gauge readings are then taken at regular time intervals. From the distance, the stress of 10 kN per meter square is applied. The dial gauge, which is seen in the figure, these readings are taken at elapsed time of 0, 1, 4, 9, 16, 25, 36, 49, 60, 64, 80, 100 and 120 minutes, and thereafter at an hourly intervals. These elapsed times are used for convenience of plotting the time as root t in the square root time fitting method for determining the coefficient of consolidation, as we have studied in the previous lectures. So each load increment is maintained and dial gauge reading are normally taken for 24 hours or until the consolidation of the soil specimen is completed, as indicated by the negligible difference in successive dial gauge reading or whichever is late. The final dial gauge reading is taken just before the load increment. The next load increment is applied. After this, the next load increment is applied and the dial gauge readings are taken in the previous load increment. After the consolidation of the specimen is completed, under the maximum stress of 800 kN per meter square, the load is gradually removed, maintaining a load decrement ratio of 1:4. Thus, loads are removed in such a way as the stress is 250 and 10 kN per meter square, and then the load is completely removed. Each stress increment during unloading is again maintained for 24 hours. The soil specimen is allowed to swell and the dial gauge readings are taken at the same elapsed times as we have discussed it, and or at hourly intervals. After the load is completely removed, the consolidation cell is dismantled and the soil specimen is taken out. The final thickness of the sample, the weight of the sample and the dry weight are determined and then recorded. So, what are the things or what are the parameters that can be determined from this consolidation test? We can determine the coefficient of consolidation or we can determine the void ratio from this test. So how to determine the void ratio? Normally the equilibrium void ratio at the end of the consolidation under each load increment is determined from the initial and the final dial gauge readings under the stress increment by using any of the two methods. So these are two methods are change in the void ratio method and the other is height of the solid method. So let us go through the first method. What is the change in void ratio method? In this method, the change in void ratio under the last stress decrement is computed and is subtracted from the final void ratio to determine the void ratio at the beginning of the last stress increment. So under each stress decrement or increment, it is determined by working backward from the final stress to initial stress. Hence the void ratio obtained from this relation as Et equals to G into Wf divided by S or equal to G into W into F. When the soil specimen is fully saturated and the degree of saturation is 1, where WF is the final water content of the soil specimen, at the end of the consolidation test, already we know from the coefficient of volume change that delta H by HF is equal to delta E by 1 plus delta T. So from this relation, the change in void ratio is obtained as delta E equals to 1 plus ET divided by HF into delta H. This is the main formula for calculation of settlement in the soil, where HF is the final thickness of the soil specimen at the end of the consolidation test. So from this method we can easily find out the change in void ratio of the soil sample. And next method is the height of solid method. How can we find out the void ratio from the height of solid method? This height of solids, which is constant for the given soil specimen, is computed from the relation as Wt divided by G rho W divided by A equals to Wt divided by G rho W into A, where Hs is the volume of the soil solids by cross-sectional area of the soil specimen. So, the change in the thickness of the soil specimen is determined from the following relation as delta H equals to R0 minus Rf multiplied by 0.002, where R0 is the initial dial gauge reading under the given stress increment, Rf is the final dial gauge reading under the given stress increment, and 0.002 is the least count of the dial gauge, as we have already told in the lectures, and it is in millimeter. So delta H is in millimeter. Hence the height of the sample can be obtained as H equals to H0 minus delta HP, or therefore H equals to HF plus delta H. Hence the void ratio is given as E equals to volume of void by volume of solid, as we have studied previously during the soil mechanics 1. And we can deduce the formula by writing H minus Hs divided by Hs. Hence, here we can find out the volume or the void ratio of the soil from the height of solid method. Next, we will go to determination of coefficient of consolidation. So, from the consolidation test, we can easily find out the coefficient of consolidation. So, the coefficient of consolidation under each stress increment may be determined from any of the following three methods. Normally, these three methods are used for finding out the coefficient of consolidation. So, these three methods are improved rectangular hyperbola method, square root of time fitting method, logarithm of time fitting method. So, we will study thoroughly these three methods consecutively and how to find out the coefficient of consolidation. So, first of all, let us go through the improved rectangular hyperbola method. The improved rectangular hyperbola method is observed to be very simple, consistent, and reliable for determination of coefficient of consolidation. So, let us discuss how the test is being carried out. So, this test is being carried out by plotting a graph. You can see the graph where time is on the x-axis and time by displacement t by d is on the y-axis. So after an initial curved portion, the graph gives a straight line portion in the range where u equals to 60 to 90, as we can see in the graph. The straight line portion in the range of u equals to 60 to 90 is extended backwards to the y-axis, as we can see in the graph. The slope m and the intercept on the y-axis c of this extended straight lines are determined. Then the coefficient of consolidation is determined from the relationship CV equals to Bm d square divided by C, where CV is the coefficient of consolidation and it depends on time and depth of the sample and height of the sample, and B is the constant which is equals to 0.297. M is the slope of the extended straight line portion of T versus TD plot, and C is the y-intercept of the extended straight line portion of the T versus TD plot, and D is the length of the drainage path. It is observed that the straight line portion of the required for this method is readily obtained for a wide range of soil. Hence, this method is found to be consistent and reliable for determination of the coefficient of consolidation in most of the situations. Also, the method makes it easy to program the calculation of consolidation results, including the coefficient of consolidation, without necessarily plotting a graph of t versus td plot. So the next method, the second method, which is known as square root of time fitting method. So this method is suggested normally by Taylor, and it is based on the observation that the time factor corresponding to 90% consolidation, or T90, is equal to 1.15 times the time factor required for 60% consolidation, that is T60. So here is the graph for square root of time fitting method. So how this is being carried out? So let us plot a graph between root t and dial gauge reading, and with the given stress increment. So this figure shows the root t and r plot. So what is being done? The initial straight line portion is extended of the curve backward to meet the y-axis. The point of intersection of this line with the y-axis gives the corrected zero dial gauge reading RC. So from RC, we can draw a straight line such that its abscissa at any point is 1.15 times that of the initial straight line portion of the consolidation curve. The intersection of this line with the consolidation curve gives a point P corresponding to 90% consolidation. The abscissa of the point P gives root over of T90. Then the coefficient of consolidation can be computed from the relation CV equals to T90 into D square divided by small t90, where capital T90 is the time factor corresponding to 90% degree of consolidation, which is also equals to minus 0.9332 log of 10 into 1 minus 0.9 minus 0.0851, whose value is given by 0.8481, when D is the length of the drainage path, that is h by 2, where h is the average thickness of the soil specimen in the given stress increment. This method is mainly suitable for the soil that gives a consolidation curve with an initial straight line portion. And the last but not the least is the logarithmic time fitting method. This method was mainly suggested by Casagrande based on the observation that the intersection of the straight line portion, that is log t and u relation, and the asymptote of the lower portion gives the point corresponding to 100% degree of consolidation. So how the test is being carried out? So this is the graph of logarithmic time fitting method. First, what we need to do? We have to plot the time dial gauge reading for the given stress increment with time on the x-axis on log scale whose base is 10, and the dial gauge reading on the y-axis. Then we have to measure the vertical distance A on the curve between points corresponding to the time t equals to 1 minute and t equals to 4 minutes. The corrected dial gauge reading RC is obtained by drawing a horizontal line at a vertical distance above the point corresponding to t equals to 1 minute. The consolidation curve log t versus r consists of two straight line portions at each end with a curve joining the straight line ends. Extend the two straight line portions to intersect at point P. The abscissa or the x-coordinate of the point P gives the time corresponding to 100% consolidation, that is T100 on the log scale, and the ordinate gives R100. The dial gauge reading corresponding to 50% consolidation, that is R50, is obtained from the relation as RC minus R50 is equals to half of RC minus R100. The abscissa or the x-coordinate of the point corresponding to the R50 on the consolidation curve gives the time corresponding to 50% consolidation. So here we can compute the coefficient of consolidation from the relation CV equals to T50 into D square divided by small t50, where capital T50 is the time factor corresponding to 50 degree of consolidation, and this time T50 degree is given by pi by 4 into the percentage or degree of the consolidation square, that is pi by 4 into 50 by 100 whole square, whose value is given by 0.1963. Here small d is the length of the drainage path and h is the average thickness of the soil specimen in the given stress increment. This logarithmic of time fitting method requires the time dial gauge readings in the secondary consolidation range beyond 100% degree of consolidation. And lastly, how to determine the permeability of the soil. So, from the consolidation test, not only we can easily find out the void ratio change or the coefficient of consolidation, we can also determine the permeability of the soil. So, the permeability of the soil specimen under any given stress increment can be calculated from the coefficient of consolidation using the relation. So, this relation we have studied in the previous classes, where K is given by CV into MV into gamma W, where CV is the coefficient of consolidation, MV is the coefficient of volume change, and gamma W is the unit weight of the water. So hence these are the parameters which can be measured from coefficient of consolidation. So the consolidation chapters comprised of all these parameters along with its settlement and the test procedure. Thank you.